Hello, everyone. I'm going to talk about using deep learning techniques for climate downscaling. And this is a true collaboration between climate scientists and computing scientists at the Oregon between Environmental Science Division and data and science learning and mathematics and computing science. The motivation. First of all, what is downscaling? I think most of all knows. So it is either physics-based or statistical based process that generating high resolution data using low resolution data. And why we want to do the downscaling using deep learning? Are there any other ways that for doing this kind of thing? So as you know, there are dynamical downscaling and the statistical downscaling, and they both have their pros and cons. And particularly the dynamical downscaling is physics-based, but it is computationally expensive. And the statistical downscaling is cheaper, but it is constrained by the availability of observations. For example, for regions with sparse data, such as the mountain regions, where the weather actually is influenced by the terrain a lot. And also a very important assumption in statistical downscaling is it has to assume that the bias of the global climate model to be downscaled is not changing. In other words, they assume the climate state is stationary, which is not reasonable. So these limits or limitations motivate the scientists to think about other ways to do some downscaling, such as the deep learning approach. And this approach don't have to rely on observations, so it can work on many variables, not only precipitation or temperature, like the typical statistical downscaling can do. Moreover, it would cost much less computing resource, so one can generate actually more ensemble members for understanding model uncertainties, for example, for future projections. Oops, sorry. This looks not right. I don't know why the figure didn't come out. Okay, I'll just talk about it. So one of the deep learning approaches for downscaling is so-called the SuperResolution Model, which I intend to show in this slides, but somehow it didn't come out. Assume you have lots of low resolution pictures, and you will be able to generate high resolution pictures using this so-called super resolution model. And for statistical downscaling specifically, the state of the art of super resolution is developed as the following. I'll talk about which. So first of all, it will take a high resolution, high fidelity data set to serve the ground truth. And here I was going to talk about a data set that developed by Encoder. It's a wind-to-kit data at a gray spacing of 2 kilometers. It's a published paper, actually, if you're interested. And the second step, they would aggregate this high resolution data to a low resolution and then based on the original high resolution data and the aggregate low resolution data, they will be able to develop a so-called super resolution model based on CNN, which usually used for images. And then the super resolution model is applied to a data set such as GCM, which you can imagine I was going to show on the right. So for this GCM with the super resolution model, you can generate high resolution data with lots of features actually. but the problem is because this data set, for example, they use CCSM data set, they generate the high resolution for the CCSM data, but because there is no true data involved during this production, so the high resolution data actually is not validated, and so there would be some challenges using this data, although there are lots of fine features. So what motivates us here is instead of building a super resolution model based on a high resolution data set, and then apply to a global climate model for high resolution, can we build a bridge to directly learn the relationship between the high resolution and the low resolution regional climate model output? So if one has a low resolution regional model run, they can use this bridge to generate high resolution data. And this high resolution data should be reliable enough. By reliable, we mean it should be close to observation, but we also don't want to constrain ourselves to observations because there are limitations about the availability. So we target to some high spatial resolution data such as convective permitting scale, such as 4 kilometer or less, because many study has shown this convective permitting scale actually can do a much better job for convective systems and coarse resolution, but there are some challenges, as I will talk in a minute. So there are challenges in those data sets. So we actually start our exercise as we present here based on a data set at 5 kilometer versus 12 kilometer data set. The challenges are, as you can see,
if you'd like, we could probably present for you since maybe the images will work on ours.
Yeah, let's do that because seems like this animation never works. Sorry about that.
I'll just share on mine real quick and hopefully we'll... Just tell me when to forward it back.
Yeah, that's good. Thanks. So you can see on the right, those images, which is 5 kilometer and the 12 kilometer. You can see those the difference of those two images, which are from exactly the same time step. They're not only different in resolution. In other words, we are looking at a problem that not dog to dog or cat to cat. Actually, it's something like dog to cat problem because our high and low resolution data, they are not aligned with each other. And also in typical imaging problem, such as we look at the human face or animals, we know where the eyes are or the noses are. So you know where to tackle the resolution problem. But here we do not have that prior information. So that's the other challenges we're facing here. Eventually, our ultimate goal is that to apply this deep learning model on the fly to a coarse resolution regional climate run, where you can generate high resolution climate data for both historical and future projection, but you only cost a much less computing resource. But the data is still based on physics because we are working on dynamical downscaling data set. So we can generate more ensemble runs to understand uncertainty. Next slide, please. So here are the two CNNs we developed, and I'm going to show the flow chart in a second, but here let's talk about the input and output first. As you can see, the table We use coarse resolution precipitation data. We focus on precipitation, by the way. Sorry if I didn't mention that before. And we use high resolution terrain height. In addition, we consider other variables as conditions for precipitation, such as sea level pressure, vertically integrated water vapor, and temperature, which we found they have pretty good correlations in both space and time with precipitation. And you can see on the right side of the table, actually those variables are in different units and different scales. And the output is the high resolution at 12 kilometer and for precipitation. And all the data we're using here, it's a output from WRF model. It's a 1 year of simulations for both resolutions, and it's 3 hourly. So we have 2,920 images for the problem. And we use 80% of the data for training and validation and 20% for data for testing. In this case, our testing period actually is October to December, as you can see on the right for the map, when the Northwest has its largest precipitation of the year. And there are also good amount of precipitation over Southeast. Next slide, please. So here we go. This is one of the CNN we developed, which we call the stack CNN. What we mean is, as you can see from the very left, we put all the input variable, including the low resolution precipitation and the conditional variables, which are all generated by the 50-kilometer WRF model. And we use many techniques which show in between, and eventually we generate the high resolution at 12 kilometer. I would like to remind us again, this is different from the regular single image super resolution approach, which actually use the same data resource, but aggregate the high resolution data to the low resolution data as the input and generate high resolution. And talking about the techniques we used, you can see from the lower part of this slide, two techniques that I would like to highlight here. One is the so-called the inception module, which tackle the unalignment problem, as we mentioned before. Those images actually quite different, look quite different, and they're not aligned with each other in terms of the precipitation values. So what we do is we consider more pixels for each layer and eventually generate the single pixel of the output. In this case, actually, we look at a larger view of the data site data to generate the eventual image. And the second technique is this attention, which we use both spatial attention and the channel attention. For the space, we're talking about tackling the data sparsity problem, which we give higher weights for the larger values. And for the channel attention, we're showing the look at the relative importance of each data set. Next slide, please. So here we're apply an encoder to the CNN, which is very similar to the stack, but because of the different scale and unit, you can understand this, we normalize the variables and then put into the CNN, and how it works is very similar to the stack. Next slide, please. I see I only have less than 2 minutes. So for the loss function, in addition to the typical loss function, we also use the conditional gain because it can generate more realistic result and capture the sharper gradient. I can show you the results in next slide, please. And we can skip this because those are metrics we look at. We can talk about, okay, so here we compare 3 results from the CNNs, which use the normal loss function and the GAN. And you can see the GAN actually can capture the extreme precipitation pretty well and close to the ground truth. And we also look at different regions. Again, always is helpful to capture those extreme precipitation. And next slide, please. And here we're looking at each pixels instead of looking at all the pixels and the time steps as shown in the PDF. And here we look at data variability or standard deviation and also the extremes. And what you're looking at here is the top 5 precipitation amount. And you can see the GAN, when we use GAN to train the stack CNN, it improves the RMSE domain wise. If you look at the large value of precipitation, this GAN actually generate the best results compared to the ground truth. And next slide, please. And here we look at different percentile from 70% to the 99%. And we look at compare the baseline and GAN trend CNN, and also look at the other CNNs actually. And you can see the RMSE is reduced and the pattern correlation is increased. And here why we look at care about data variability and the extremes, because as you know, the extreme precipitation is a big concern, and the precipitation variability actually is also a concern because it can drive the variability of the data, and it can drive the extremes and affect the food security or stream flow or drought, all those kind of things. That's why we'll focus on that. And next slide, please. That's a summary, and I'm running out of time, and if you have questions, I can answer in the chat or here. Thank you, and sorry for all those hiccups.